So as James mentioned there, my background originally is boat building, all different types of traditional Irish boats, building them, repairing them, about 25 years, and as well as that, sailing them. So a lot of experience with boats and ships, and hopefully this whole talk is going to be about boats and ships, so hopefully we don't make anyone too seasick by the end of it. So as James mentioned, part of my work and hobby, I got involved with this Traditional Boats of Ireland project. I was sailing an old traditional boat myself, and at one of our boat gatherings, we started to realise a lot of the boats were down to single figures, like one of its type left in the whole country. And a lot of them were traditionally built by traditional shipwrights with no plans, no drawings, no measurements. So we created this project where we were going to document the boats around Ireland. It started in '96, it took 12 years, and the book was published in 2008. There's 60 boats in the book. Drawings, images, artist impressions, and a little bit of the ethnography about each of the boats as well, how they were used, where they were used, and sometimes how they were built. Of course, the minute the book was published, the telephone started ringing. You forgot a little boat in my back garden, or there's a boat down the back of the shed. So we had to go and document some more. Measuring and recording a boat, it's not a simple operation. There's no straight lines in a boat. It's all curves, usually curves in 3 dimensions, and quite often they're in strange places, difficult to get at, buried under ditches. So we started looking at technology as well to record it. Here's one that I recorded myself, and we actually rebuilt a full-size replica of it. So to start off with, the boat's got to be levelled and straightened up, and then you're taking all your measurements from baselines. So you're setting up vertical posts, measuring out horizontally. It takes a lot of time and a lot of accuracy to get the measurements so that you get an accurate record, all the dimensions, and eventually produce drawings and build a replica or a copy. Same with archaeological recording for shipwrecks and any sort of archaeological recording. How do we measure it? And traditionally, it was all done with control points, baselines. You set in a site datum point and you measure out to the objects, or you use grids and measure and draw based on the grid, or triangulation. So you take 3 measurements and you can replot that point using trilateration. Again, very slow and very time-consuming, particularly with large, complicated objects. Something like a building is a lot easier. You just measure 2 points and pretty much assume it's a straight wall. There is nothing straight on ships. So traditionally, this is the type of stuff we were finding: squashed and buried shipwrecks, lots and lots of timbers, lots of complicated shapes to be documented. And right up until the 1960s, there was very little actual measuring and examining of the ships. They just normally maybe draw a site plan, a little description of what they thought it had been, try and slot it into a timeline and say, it's a 12th century boat. This is an example of the Roskilde ships, which were found up in Denmark. It's a collection of 4 Viking ships. They're all from the 900, 1000. It would have been quite common in those days. They were constantly at war. Denmark, Norway, Sweden, constantly battling with each other. And quite often they sunk ships to block the entrance to a harbour, to stop the invading navy getting in. So it's quite common up there to find a large collection of ships deliberately sunk. And they're quite well preserved, so we can find out an awful lot of information about them. And of course, being up in Denmark and Vikings, the Danish government were delighted finding 4 ships. And they decided to build a Viking visitor centre. The minute they started digging the site to build their visitor centre, they found 6 more Viking ships in the site they were going to build. If anyone is interested in ships or archaeology and a nice, fascinating holiday, that Roskilde Centre now is a working museum. They have a full boatyard outside. You can actually use a replica of a Viking axe and chop open a log, carve it into a plank, traditional rope making, and go for a sail on replicas of the traditional boats as well. But at the time, this whole thing, it represented a big turning point in how the boats were recorded. One of the people working there, Ole Crumlin Pedersen, was a naval engineer, and he thought, what about if we document each of the individual parts of the boat? Maybe we can better understand how the ships are built. And they developed all sorts of methods. Again, this is before the days of laser scanning. Photogrammetry was in use a little bit, but it wasn't really accurate enough for what they were trying to do. So they're actually tracing each of the timbers onto full-size sheets of clear film and drawing all of the features on each one of the timbers. You can imagine with a ship with a couple of hundred timbers, it produces kilometres of plastic film. Those are all then reduced in Xerox machines down to a smaller, more manageable scale. And they came up with the idea of cutting out the shapes of each timber onto paper or cardboard and then sticking it back together to recreate the shape of what the ship might have looked like. The problem is, okay, they're using all the fastenings for all the timbers, so all the timbers go back together as they should have done before the ship sunk, but it's all been damaged and deformed, and you're trying to figure out what did the boat actually look like when it was in use. So basically their methodology or their workflow was stating that once a satisfactory model had been achieved, the measurements and the lines were measured from the model to produce what they were calling the construction drawings. The question is, what is a satisfactory model? How do you define that, or how do you know that you've made the right shape of the model? And then being built out of cardboard or paper, those models are very delicate, very, very difficult to measure. Like you're trying to touch a piece of paper or a piece of cardboard that's only 1 or 2 millimeters. It tends to move even while you're trying to take a measurement from it. So is that really what the ship looked like? It's somebody's interpretation of it, it's their impression of it, but we're not 100% sure. So that's when I started getting involved in the project. These were some of the other forms of measuring. Archaeology tends to be the kind of poor cousin in the social sciences, so we steal and borrow a lot of technology from other fields, so things like total stations, theodolites. Christian LeMay in 2000 experimented again up in Denmark in Christianshavn. It was an old port. They were excavating for a new building and they found a collection of 6 ships. They only had 5 days to measure all 6 ships. So he used a total station and they just marked and measured what they decided were important points on the shipwreck. And if anyone understands how a total station works, it's all angles, so it's left and right, horizontally and vertically. So you have to take 2 measurements for each point. They decided if they skipped the Z measurement, the height measurement, they could save 4 or 5 days out of all their measuring. So they plotted all the points, went back to the office and tried to reconstruct the ships that they had documented. Problem was, everything was a flat, 2-dimensional drawing. They didn't know how high or how thick timbers were, so a total failure. They also tried using the same technique down in Yenikapi in Turkey. They were building an underground metro station, and they managed to position it right where the original Roman harbour had been. They found 28 shipwrecks. There's over 6,500 individual timbers, which all had to be documented. We've been down there since consulting and teaching them the methods that we developed in Newport. So digital documentation, James just mentioned it there. It was working with the Traditional Boats of Ireland project. I was looking at things like photogrammetry, laser scanning, handheld scanning, terrestrial laser scanning, and much more detailed, accurate scanning on coordinate measuring machines. A lot of the stuff that we were measuring with the Traditional Boats of Ireland project was builders' models. So in the old days, like right up to the 1920s, 1930s, a lot of boats weren't being drawn. The traditional boat builder would carve a model out of a block of timber until he got to a stage where he was satisfied with the shape. This is where the archaeology in Roskilde was trying to emulate their approach. The difference being the boat builder had been building boats all his life and knew what a model boat should look like. So we had a lot of these builders' models, sometimes half-scale models, would just be one side of a boat, and we wanted to try and document those as well. Problem with a small-scale model, if you're taking a measurement, and these guys tended to work in imperial measurements, so 1 inch to 1 foot, so the model is 12 times smaller than the real size boat. Or for a big model, a big ship, it could be 1/4 inch, so it's 48 times smaller than the real thing. So if you're measuring something like 1 millimeter on a model that's 48 times smaller, that's 4.8 centimeters in a 1 millimeter measurement. So you can very quickly start to build errors into the measurements. That coordinate measuring machine in the corner, it's measuring at accuracies of 0.028, 28 microns. A human hair is 20 microns on average, so it will measure super accurate. We can then scale the model back to full size on the computer and look at how the thing actually sails and floats. The main thing with all this digital documentation is it's super fast and it is super accurate. We're talking millimeter accuracies. Another example there was a collection of boats up in, I'm out in Scotland. It was another museum which went bankrupt and they were selling off their collection. It was super eclectic, the collection. There was Irish currachs, there was gondolas from Venice, there was sampans from Vietnam, there was Arab dhows, all crammed into a storage shed. We had 5 days to measure over 240 boats. So we went up there to 41 laser scans in one shed, 108 laser scans in the other shed, and we have a physical digital record of that collection, which no longer exists. It was all sold off in pieces, just dispersed back to, in a lot of cases, their home countries, in some cases, private collections. So there was some very unique boats in there. One of the very first rowing Royal National Lifeboat rowboats that would have rowed out and rescued people from shipwrecks. That's some of the other work I do is commercial laser scanning. 740 laser scans, over 5 billion data points. We laser scanned the entire factory so that they could redesign and relay out their production line. So lots and lots of data which you can then break down into smaller manageable sets. Back to the scale models. This one here, we think it was built for one of the great exhibitions. It's a model of a Kinsale hooker. Some people might have heard of a Galway hooker. There had been famous workboats up around Connemara. The Kinsale hooker was more famous back in the 1800s, but it died out because English boats were coming over fishing for mackerel, and this boat was a lot bigger and slower. So the English boats could go out, catch the fish, be back in and sell them, while the poor guys down in Kinsale were still only heading out the entrance to the harbour. So they disappeared from use. The very last one known was around about 1910, 1912, and that sunk in Kinsale Harbour. But this is a very detailed, very accurate scale model which was built for one of these great exhibitions. It's up in the National Museum and we got permission to laser scan it. So again, the coordinate measuring arm, laser scanning to make the point cloud. From that, we convert the point cloud into a digital surface model over there on the right. And from that, we're able to model all of the individual timbers of the ship. So something that doesn't exist anymore, just from a scale model, we're able to recreate the reconstruction drawings, the structural drawings, how to build it, and even the sail plan. And then we're able to analyse how good or how bad that ship was, how much cargo it could carry, how far it could sail. As well as reconstructing and just recording, we can also use the technology to monitor the condition of artefacts, buildings, or objects. So that's another a boat that was built down in Baltimore in 1904, I think. We found it up in Donegal in a very sad state. Laser scanned it. We can produce the drawings, but you can see also here where the centre line, the straight dead centre of the ship, and the whole back of the boat has started to fall and distort. So we can monitor ships in museums, we can monitor buildings as they're affected and altered by weather and deterioration as well. So the thing with digging up shipwrecks and archaeology, there's 4 examples. The Sutton Hoo ship over in Suffolk, it features in the Netflix film The Dig. It's the year 640. It was excavated in 1939. There was a king buried inside it, 80-foot long ship, and the Anglo-Saxon burial hoard is still on display in the British Museum. His gold helmet, his shield, all the grave goods that were buried with him. The ship didn't survive, all the timber had disappeared, but the iron nails still survived. And because it was buried in sand, this footprint of the ship was still in the sand. So we were able to document and reconstruct the ship from old excavation records. Again, that's the Viking ships up in Roskilde, and that's the Newport ship over in Wales, which I'll talk about a little bit more. And using technology to document stuff that we can't get to. This is a project we worked on up in the Black Sea. It's a Roman shipwreck. It's 2,000 meters deep. It's so deep there's no marine bacteria, shipworm can't survive down there. It's below the anoxic layer. The ship is completely, perfectly preserved. Even the rope decoration knots tied around the mast are still there. A human being can't get down there. We sent down ROVs, took 7,000 photographs and built a digital model of the ship. And now with the VR goggles, we can go and dive on the shipwreck and actually take the measurements and examine the actual cargo is still in the boat. So you can get access to what is technically inaccessible regions. You can capture data very quickly, and you can capture data very, very accurately. Problem with archaeology and cultural heritage, any type of excavation, it's destructive by nature, so you can't go back and re-examine it afterwards. So we have a pretty serious obligation to record it as accurately as we can and in the highest possible detail, because once we've excavated it, we've disturbed the site. And there is stratigraphy in the sites. So as the layers build up over time, or as the objects are deposited in the site, you get to see how that site has developed and evolved as well, and whether it's been interfered with throughout history. Again, as I said, we tend to steal a lot of technology from other fields, so the traditional survey approaches with string measuring plumb bobs. We've tried things like GIS and 3D GIS, which is graphical information systems. You're mapping the position of objects onto a map. BIM, building information modelling, and then we tried shoehorning that into heritage building information modelling, where every piece of the object has a data tag with information attached onto it, and then onto full digital modelling. But the whole idea with the excavation, we're trying to reconstruct the past. We don't know exactly what that past looked like, so what we're creating is a hypothesis, a theory of what the ship looked like. And the problem is that hypothesis then needs to be tested so that it can remain tenable. Is it a valid assumption of what the stuff looked like? That's where I had my midlife crisis and started a PhD down in Southampton. I should have gone and bought a sports car instead. So it was this idea of the model, making the cardboard model, and when they were satisfied with how the model looked, they called it job done, they measured the model and published the drawings. How do we know? Who is the person that says it's a satisfactory model? As a boat builder, I looked at some of those models and I said, no, I think there's a mistake there somewhere. So I wanted to see, is it possible to put science into the equation? Could we test the model? Could we test the reconstruction? Here's a couple of cartoons. How we look at the object that's presented, our interpretation or our viewpoint. Are we looking at 6 or 9? Because there's no reference for up and down, both hypotheses are correct. And then how we actually illustrate the objects, again, from which viewpoint, which is the correct hypothesis. So again, how do we test, how do we validate the reconstruction? So one of the boats, and I have to confess a little bit, I built the boat and I also sailed on the boat, so I know it pretty well. But we laser scanned it, 6 scan positions, took an hour and a half, a couple of million data points. That's a video fly through of the point cloud. You can see as well, you capture an awful lot of extra detail as well as the actual object you're interested in. So we have some of the other ships in the yard. Now we have big problems with GDPR because you also laser scan every person that walks past. So you've got to go in and clean those people out of your scan data. But we're then able to crop out just the object of interest, in this case, this lobster fishing boat from West Cork. So we know exactly how the boat floats, how it sits in the water. We have the painted waterline and the actual mark of where the water is sitting on the boat. So good old Archimedes, trying to work out the weight of the king's crown in the vat of water, figured out a body floating in water displaces its own weight. Using the same technology applied to a ship, we know where the boat sits in the water, we know the angle it sits at. That volume of water tells us the exact weight of the ship. So we set up the digital model exactly as the real model floats, and that gave me the reference, the baseline datum point. Then made a digital model of the ship. So we recreated every single timber in the ship, and we're able to apply materials using the 3D modeling software. We can tell the ship that that piece of timber is oak. It can then calculate the center of gravity, the weight, and the actual dimensions, characteristics of the materials, add them all together, and the naval architecture software, it's called Orca 3D, will take that information and it will orientate and position the ship as it would float in a real-world environment. So when we plug all the information into the various bits of software, adding in all the extra details as well, we get these type of results. So the very faint one at the top there, it's just the timber of the ship, nothing else in there. Then I added in the life raft, the anchor, the ropes, all the extra bits, the sails. And slowly but surely, the digital model came right down to almost exactly the same point. It's actually 98.8% accurate for how the boat sits in the digital model compared to how the real-world boat sits. I was also able to run it through some software in Unity and apply physics and get the boat sailing very, very similar to how it sailed in real world. So we're recreating the real-world object in a digital environment. We can then take that and apply it to archaeological shipwrecks and reconstructions, so we're now able to test the validity. Does the shipwreck that we've created as a digital hypothesis, does it actually float? A lot of the earlier ones, which I researched as part of my PhD, didn't float and definitely didn't carry the amount of cargo that people were claiming they could carry. So Dick Steffi, who was a famous lecturer over in Texas A&M, they would have been a kind of a world authority on ship reconstruction. He was also a ship model builder, so he knew the kind of stuff he was talking about. And in his book, he said nothing that a sunken ship was carrying, all of the fancy bits of pirate treasure, the lovely amphora jars, nothing touched as many people as the actual ship itself, the building of the ship. And that's what we're interested in, is the people who built it, the people who used it, the equipment, the materials that went into building it. And that's why we're going into so much detail in the reconstruction and the analysing of the ships. So using just the Newport ship there as a case study, it was found in Newport over in Wales. This would have been the old medieval town of Newport. The ship was from somewhere around about 1449. We used dendrochronology to date the timber. We know all the timber came from the Basque country. So the ship was actively trading between the Iberian Peninsula and the Bristol Channel. We have a lot of the staves from the wooden barrels or casks. So the Dunster's shopping bag, the bag for life back in medieval England, was these wooden barrels. And we were able to analyse, using other specialists, what the actual remains were inside the barrels. So we know in quite a lot of detail what was being transported and carried around. So this ship was discovered in 2002. Again, it was very early days for laser scanning. A laser scanner at the time was a couple of £100,000. They didn't have access to those. They did use some photogrammetry, stereo paired photographs, and you can recreate the 3D shape from those photographs. But they also used the traditional documentation, the offsets, baselines, survey grids. You can see one of the survey grids in here, and offset measurements. So hand-drawn documentation. The site had been surveyed beforehand, because that whole area, Caerleon, Newport, it's been in existence since before Roman times. The underground survey, the sonar study said there's nothing there, so they started building the site. It was a riverfront theatre, and this is the area for the orchestra pit. They'd already put in the concrete columns, and they'd literally pinned the ship to the ground 7 meters below the surface. They even managed to get one of the columns right into the position where the mast would be in the ship. So the shipwreck was pinned in position with these concrete pillars. The only way to get it out and document it was dismantle every single timber, all 3,800 of them, and over 1,000 separate artefacts, things like shoes, hourglasses, stone cannonballs. So a massive collection of human activity from the Iberian up to the Bristol Channel. and crossing nearly 100 years of time period. We were able to date some of the timbers that supported the ship and some of the timbers that were actually put in as repairs to the ship. So a massive database of information. So the project split into 2 stages, the excavation documentation, so they surveyed the site, and then post-excavation documentation. And here's the warehouse they rented with 3,200 ships, timbers, all inside in tanks of water to keep them moist. The minute they start to dry out, they shrink. So we're keeping them stable in water, treating them and conserving them, and then documenting each one of the timbers. So again, using that coordinate measuring arm, and we're tracing the timber, the outline shape of the timber. It's drawing then in 3 dimensions onto the computer screen the shape of each timber. But as well as the size and shape of the timber, we're also documenting things like the marks that the builder made. So he scratched the number 4 here in Roman numerals on the ship. Positions of the fastenings, the nail holes, and things like wood grain, things like damaged edges on the timber. So a massive amount of data is being recorded onto layers. That allows us to publish the traditional 2-dimensional timber catalogues that go with any shipwreck. But it also lets us create digital models of each one of the timbers. So we brought all of that data back together into a digital model to start this idea of reconstructing the ship. So you can see here we haven't used the old approach of flattening out onto cardboard and paper. We actually have 3-dimensional digital data, but it's still all just flattened out. It's all fallen apart because it's all been documented separately. We know each timber as it's related to the one it should be connected to, and we've recorded all the nail holes. And thanks to the technology and the beauty of 3D modelling, we're able to create a solid digital file of each timber, and we're able to use 3D printing. So we 3D printed at 1:10 scale every one of the 3,000 timbers, and someone had the fun task of a 3,000-piece, 3-dimensional medieval jigsaw puzzle. And to give you an idea of the size, that's an English penny. And these are the tiny little jewellery screw watch screws that we're using to attach the timbers back together and build it back up into a physical model. It's 1/10 of its size, so the model itself is over 3.5 meters long. That's when I joined the project in 2008. And at that point, again, they were stuck. Even that digital or physical plastic model, it was very fragile. It moved a lot when you touched it. Some of the planks were only 2 or 3 millimeters in thickness. So I said to them, well, let's laser scan it with the coordinate measuring arm. So we're not touching the model. We're using non-contact digitizing. So we laser scanned the physical scale model and brought it back into the computer. And then they asked me, could I reconstruct their ship? Pat Tanner was the expert that could build ships from digital models. So I got stuck into this project for 5 years. And again, all that masses of data, bring it all together into one digital file so you're not rooting through archives. Where did the sketch from the 14th of August when we dug up that piece of timber? We got it all together into one file. And you're then able to look at how things match and how things go together. And we just kept repairing, modifying, bending back together and rebuilding the ship. So we've rebuilt the ship as a digital model in full size. And we also have all of the builder's marks, the measurements, the scratches, the damage. So it's a massive 3D digital archive all in one space. You can walk around inside the ship now and you can see where the builder has put a measurement on the hull of the ship to mark either a measurement he was making or a place for another timber to go in. And again, building the whole thing up. Back to this idea of how do we trust, how do we believe the hypothesis? Anything on a computer screen, anything as a digital model, there's this sort of belief a computer has made it. It's more authentic, it's more original than an artist's impression, which was the original way of showing the reconstructions. If a computer has done it, it must be correct. So we now have an obligation to try and avoid this, what we're starting to call hyper-reality, or it's more than real life. So just simple color coding. Everything in brown was the original timber that we found. The blue here has to be there to keep the water out of the ship so that it can float. Green, we have evidence that it should be there, so the mast for the ship. We know the base of the mast is there, so there must be at least one mast. And then everything in red is taken from iconography or comparative sources, a similar shipwreck, a historical document, or a contemporary image. One of the problems with Newport ship, most ships tend to sink out at sea. Newport ship sunk in the harbour in Newport while it was being repaired, and right alongside of it was a woodworking yard. So there was a risk of site contamination, and there was a lot of objects dumped in. It became the medieval tipping ground. After they couldn't use the ship anymore, they salvaged what they could reclaim and used it to build walls and fences of medieval Newport. But it also became the dumping ground for the town, where they dumped a lot of trash in there. So this is all of the articulated timbers, everything that's still nailed together and attached to each other. And over here, a map of the disarticulated timbers, all the loose stuff that was dumped in. So that brings us on to this idea of minimum and capital reconstruction. So for the minimum reconstruction, we used only the articulated timbers, only stuff that was still physically bolted to each other. And we got to a ship of this dimensions, again, all colour-coded for clarity or for hold up your hand honesty. And then the capital reconstruction, where we're starting to use the loose timbers and building up more and more of a concept of the ship. Some of the iconography from the time, museum models, images from the Beauchamp pageant, and again, building up what we think might have been there on the ship. And then, using my scientific approach, the 3D analysis, the naval architecture analysis, can that ship float? How far can it sail? How much cargo can it carry? And that allows us to reconstruct what the ship might have been capable of doing. All the barrels are reconstructed from the timber staves that we found in the site. We know there was 3 different dimensions of barrels: a pipe, a last, and a ton, which was the medieval measurement. We have historical documents referencing those measurements. So we knew we were getting pretty close to, or as close as we could get to, what was there without actually having a time machine to go back and look at the site. So looking at historical references, when the masts appeared throughout history, we were able to add more to the ship. And again, as we added each part, we reanalyzed. So it's an iterative process. We add a second mast. What will happen in a storm? Will the ship capsize? So looking at wind loading, cargo loading, and sea conditions, and just building up the picture, adding more and more pieces. Here, the disarticulated timbers going in. That red knee there was an English timber, so we know the ship was in the middle of being some sort of a big repair job. That timber on its own is 2.5 meters tall and 3 meters long. It's a massive oak knee. And again, just building up the model layer by layer, adding in more information, adding in more of the loose timbers, and comparing the actual timber itself, the way it's been worked. Is it contemporary to the ship? And obviously, in digital modelling, you're able to use these magic skyhooks that'll let things float in space, which we couldn't put into the physical model because there was nothing to attach them to. And just building up until we get to the absolute maximum possible size based on the material that's there. Then again, going back to the iconography, contemporary with the period, and trying to match up our digital reconstruction with this will be from the Beauchamp pageant, which is 1475. So very similar time period to the ship. And then again, analyse it all, test it with Orca, see does it float, see what it can carry, and just build up a better understanding of the ship. So what we're hoping is we get to a more definitive hypothesis, which we have now used science and technology to test and verify as well. The beauty, again, with all this digital data, we're not limited to the old traditional publications, the written word and the 2-dimensional drawings. We can do 3D visualizations. I've sent my digital model onto artists who've done artistic impressions of it. And we can do nice, fancy posters with images and text for the museums. And with other technology like the Microsoft HoloLens, we can use augmented reality and bring the ship into our physical world here, walk around and have a look at it. Or with virtual reality, you can actually walk the decks of the ship now and see where the builder has made the mark on the piece of timber. And it does add more and more to the research. At one point, I put the deck in here on the ship. I put on the VR goggles, walked along, and I had to look under the beam. Oh, that beam's got to go at least 200 centimetres higher. So you get to see and understand the ship in more detail. Again, some of the other work I've done is not just working on shipwrecks, but working from archive data. So that was the Sutton Hoo ship, excavated in 1939, re-excavated in 1960. Again, we had two different versions because two different people had interpreted the data with two different versions of the ship. So I took both sets of data, combined them together, and found the matches and the dissimilarities between the two sets, and tried to solve our problem with our two friends down here on the bottom of how we're viewing the data. There was some big differences. There's 42 less people would fit into one ship compared to the other. So again, it's trying to test the hypothesis and validate it. Monitoring ships in museums, that's the Bremer cog up in Bremerhaven, built in 1207. It's one of the most complete shipwrecks we found. They put it on display in the museum, but they didn't want any supports. They wanted stainless steel cables holding it up to the roof. Problem is the steel cable stretched and the whole ship started to deform and bend in the museum. They asked me to go in and give an idea of what shape to put it back to. So I had to go back through their paper archive records. We also laser scanned it. We did a photogrammetry model of it over a period of 3 years, and we were able to see the ship physically changing and actually melting down onto the ground as it was fighting with gravity, basically. That's some of the shipwreck reconstruction from the paper archives. So again, errors in some of the dimensions, errors in how it was drawn on the paper, ends up with a very strange looking ship. And then comparing the different versions, again, trying to resolve differences between the different records. Another ship is Punic, so it's 200 BC, down in Sicily, in Marsala. It was part of the Agadi Island battle. It's been on display in a museum since 1980, and again, the same problem. Insufficient supports, the timbers are sagging in between the structural steel. And what we actually discovered from that project, it's no longer timber because we've conserved it. We've taken all the water out of the timber and we've replaced it with wax. The wax is allowing the fibres in the timber to slide. So what we've got is a jelly-like substance that looks like timber, but it's not able to span the 1 metre between the metal supports, which timber easily would do. So that's part of the research project I'm doing with Swansea. We're trying to redesign and re-engineer a new support cradle. So again, same technology, 70 or 80 laser scans, crop out the ship. There was some disarticulated parts. They'd made fibre moulds of parts of the timber when they'd excavated it in 1980. We laser scanned those. That let us again combine all of the digital data, so again building up on our understanding of what was there and then analysing it. So here I've put a perfectly smooth surface through all the support structure, and you can see all the areas where what we thought was timber, where there's now a jelly-like substance sagging out through the supports. So we need to put in either additional supports or redesign some new type of support structure for the ship. The underwater stuff up in the Black Sea, 2 kilometres deep. You can't get down there. The amount of information we've got from that one shipwreck is just mind-boggling. I'm still waiting to get my hands on the raw data to make a digital model of it. That's just an example of some of the photographs. I'm not sure if you can see the knot on the mast. It's in there somewhere, but just absolutely mind-boggling. Even the toolbox belonged to the carpenter is still inside in the mud inside the ship. Metadata and paradata, so that's what we're using to validate what we're doing. Metadata is describing the object itself. The paradata is describing what we've done, how we've gotten to the reconstruction, the digital human decision-making process. So there's the Newport ship again. There's our metadata. So just for any one of the timbers, these are all the pieces of information that are feeding into that one piece of timber. The original documentation file, its position in the ship, its digital printing file, its original record when they found it out on site, and photographs that were taken during the documentation process. And then the paradata is the actual report. So we've clearly, anytime we've made a decision with a missing part, we put a big solid line in the report. We are making a decision here. So if you don't like the steps that I've used to get to my version of the ship, you can rewind back to where you still agree with me and then go off in a new direction. All of that, all of the paradata, all of the digital files, all of the raw data is online with the ADS. So anyone here can download the data and start a whole new board ship reconstruction if you have 5 years to spare. And again, ways of displaying, visualizing the data, passive where it's written or just a simple image, or interactive with the virtual and the augmented reality. And you'd be glad to know it's not all boring, horrible archaeology. Damien Hirst, a rather controversial artist who conserved a cow in formaldehyde, contacted us in Southampton and said, I need a Roman shipwreck. I said, yeah, there's a few of them around. He said, no, I need a very specific one. He was putting on an exhibition over in Venice for the Biennale, and he had made all the cargo, over 108 objects, and he'd made them full size as works of art. They were all for sale after the exhibition. He wanted a Roman ship that could carry that cargo, and it had to sink in Zanzibar. And we said, why Zanzibar? That's where I've been hiding the stuff for 10 years, in the ocean. The actual models he'd made, huge bronze sculptures, he was throwing them over the side of a ship so that the barnacles and the seaweed would grow onto the objects. And then they were put on display in the museum. It was a surreal thing. You didn't know whether you were in an archaeological site or an artist's impression or an exhibition. It was a little bit unnerving, some of it. So we started off with just a digital model, very simply, of each of the objects, just a box representing the size. Put them roughly into a ship shape. And straight away it became apparent this was an unbelievable ship. It was going to be bigger than anything we'd ever seen. So we created an architectural impression of an artist's impression of what a Roman ship might have been like. Massive, 61 meters in length. The biggest Roman ship we'd ever seen was 40 meters. And we had to create this whole story of how this slave had earned his freedom. He was heading over to Myas somewhere here. They had a storm, and the ship ended up down in Zanzibar, where he had been hiding all the treasure for the last 10 years. I got to make a nice digital model of the ship. We ended up laser scanning all of the artifacts, massive statues. I mean, one of those is a demon with a bowl. It's 4 stories tall in bronze. And he wanted all of that to fit in the ship, as well as this obelisk of failure, which was 42 meters long. The obelisk on its own weighed nearly 100 tons. But again, using the software, we were able to analyze the weight of each of the objects and say yes or no to the ship sinking. Here's the opening of the exhibition. There's one of the statues, a snake fighting with a lion. You can see there's 2 people. That's the scale of the object. It's a massive, unbelievable scale. And that's an actual physical model of the ship on display over in Venice in the Biennale. And the nice part is we got invited to the opening and the after-opening party, where he flew in the Red Hot Chili Peppers for a private party. And that's the kind of fun stuff we get to work on. And that's just some examples of ways we can view the digital data afterwards. So things like Sketchfab, you can spin around the model, look at it from any angle. Story maps, where you can interact with the site plan. And the augmented reality, where you're using your phone or your iPad to bring the virtual digital model into our real world. And I think that's it. Thank you.